multiplication principle for events in m different ways and E2 occurring in n different ways. Then if we take E1 and E2 sequentially, so then event E1 followed by event E2 can occur in m times n different ways. So if I have 2 shoes and 3 pants, then there are 6 different ways to choose 1 shoe and 1 pant. And so suppose you have 2 shoes, shoe 1 and shoe 2, and you have 3 pairs of pants, pant 1, pant 2, pant 3. Well, with the first pair of shoes, you can choose either 1, 2, or 3 pants, or with the second shoe, you can choose, well, pant 1, pant 2, or pant 3. So therefore, the differing ways you can choose your combination of shoes and pants is first shoe, first pant, first shoe, second pant, first shoe, third pant, second shoe, first pant, second shoe, second pant, second shoe, third pant. Okay, and so there are 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2 times 1, 2, 3, 60. So the 3 plus 3 plus 3, etc. So that's the m times n differing ways. Permutation. A permutation of k objects out of n objects is an ordered list of k objects out of the n objects. The number of different permutations with n distinct objects taking k at a time without repetition is p well, A. So this is NPK. So this n times n minus 1 times n minus 2 times dot, 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 n minus k plus 1. So I'm starting out with n. I keep multiplying by 1 less, and I do this k times. This is n factorial over n minus k factorial. What is factorial? So one way of writing this is in terms of factorials. So I guess I have to tell you what a factorial is. So a factorial, maybe I'll put it like that. So a factorial is defined as follows. So this little explanation point means factorial. So 0 factorial is 1. N factorial is just n times n minus 1 factorial for any natural number n. An example, 3 factorial. Well, let's use this definition, this recursive definition for defining the idea of a factorial. So 3 times 2 factorial, 3 minus 2. 2 factorial is 2 times 1 factorial. 1 factorial is 1 times 0 factorial, but 0 factorial is 1. And so now we just have numbers. 3 times 2 times 1, 6. Let's see. Okay, good. Actually, on a graphing calculator, it's actually kind of difficult to calculate this, just because their location is not so easy. On a cheaper calculator, you can find factorials easily as compared to on a TI 83, 84, where they're hidden. Oh boy, it's taking a long time. So let's just do, okay, so clear. Okay, so let's clear this. Okay, so start out. Okay, good, finally, it's clear. Let's do, let's say, 5 factorial. So I do 5, go to math, go to probability, PRB, and the fourth one down is the factorial. So 5 factorial is 120. So that's one way of finding the factorial, is to use a calculator. Okay, so circular arrangement in n-1 ways to arrange n things in a circle. Okay, so let's try that. So example, how many ways can you arrange 5 people to be seated on a circular table? And so you have a circular table here. And you want to arrange 5 different people on the circling table. So 1, 2, 3, 4, 5. Okay, so there, so you have a circular table here, and you want to figure out, well, how many different ways can you do this? So in this case, it's just going to be 5 minus 1 factorial. And so 4 factorial is 24. Combination. Combination of k objects out of n possible objects is a list of arrangements of k objects out of n possible objects. And this is without regard to order. And so maybe I should say that. This is without regard to order. Many times you don't care who you choose first. As long as the object is selected. So NCK is n factorial over k factorial, n minus k factorial. It is npk over k factorial. It is sometimes denoted by n, and so there'll be an n here floating over a k in a parentheses. So it's not a fraction. You do not put a bar or anything. It's 2 numbers floating above each other. So it's like an 8 and a 3, and then you put a bracket. So you do not put any sort of division bar or anything of that sort. It's not division, it's the binomial coefficient. Let me tell you about Pascal's triangle. We'll be doing much more of it in section, I think, 8.1. But let me just say, to construct Pascal's triangle, you'd start it with a 1, and then go down, do a 1 and drop down the 1s on the outside of your triangle, drop down the 1, and then add the 1s above. 1 plus 1 is 2. Drop down the 1, 1 plus 2, 3. 2 plus 1, 3. Drop down to 1. Drop down to 1, 4, 6, 4. Drop down to 1. Drop down to 1. 1 plus 4, 5. 4 plus 6, 10. 6 plus 4, 10. 4 plus 1, 5. Drop down to 1. And you keep going. Okay. Now, it turns out that if you start counting at 0, so this is 0, 1, 2, 3, 4, 5, counting down the number of rows, and then go over this way for the k, starting at 0, so 0, 1, 2, 3, 4, 5, then this will give you the binomial coefficient n sub k. N ck is just found is just part of Pascal's triangle. So, example 5c3. So you go 0, 1, 2, 3, 4, 5, C3, 0, 1, 2, 3. This number, 10, is 10, there it is 5C3. I can write 5C3 as a binomial coefficient or as 5C3 because that is how it will be denoted on the calculator. 5, math, go back to, in this case, right below the factorial. They're almost always located near the factorials. 3 is 10. And so we get, just plug into the calculator, same number 10 that we found from Pascal's triangle, or use the fact that it is NCR, is n factorial over r factorial, n minus r factorial. So 5 factorial over 3 factorial, 5 minus 3 is 2 factorial. 5 factorial, 5 times 4 times 3 times 2 times 1. 3 factorial, 3 times 2 times 1. 2 factorial, 2 times 1. The 2 factorials cancel. So I get 5 times 4 times 3 over 3 times 2 times 1. 3's cancel. 20 divided by 2 is 10. So I just get 10. Let me do as an example 15C2. Let me do this by hand, but let's do it a nicer way. And so 15C2 is just 15P2 over 2 factorial. So I can think of it this way. To calculate 15C2, I do 15P2, which is 15 times 14, over 2 factorial, which is 2 times 1. So 15, I start at the 15. 2, I write down 2 numbers, 15 times 14. So I start at the number, and I keep multiplying by 1 less till I've gotten this number of numbers here, 2 of them, over, well, there are 2 numbers, so I just do 2 times 1. If there are 3 numbers, I do 3 factorial, 3 times 2 times 1. And so 14 divided by 2 is 7, times 15 is 105. So this is an easy way of calculating this. Okay, so let me do some examples. On page 769, evaluate each expression. And so 8, so this is a weird notation they have in the book, a fairly non-standard notation. Well, it's non-standard, but it's in some computer programs, they actually have that as a function written this way. So C83, which is 8C3, or 8C3. So let's calculate this. 8 times 7 times 6. Remember, you start out with 8. You write down 3 numbers over. Well, they had 3 numbers, so I do 3 factorial. 3 times 2 times 1. Well, the 3 times 2 times 1 and the 6 cancels. And so I just get 8 times 5, which is 56. 8 times 7, which is 56. And that's your answer. Let me do problem 28. And so this is 100, choose 99. Okay, so well, it turns out that you can actually calculate this much easier than doing 100 times 99 to do 99 numbers. You can use the fact that Pascal's triangle is symmetric. So looking on this side is the same as looking on that side. And so rather than, well, let's do a 100C99, let's go on this side, do 100C1. So let's do that instead. So instead of doing this number, I'm going to do this number. And so this is equal to, well, you do 100, you keep multiplying until you've written down one number. Well, that's it. Oh, actually, let me write it this way as a 100C1. So I start out with 100, only write down one number, divided by 1. So my final answer is 100. Okay. Please note, if I try to write this, my properties. If I try to do this as follows, say on the definition of NCR, it was n factorial over r factorial times n minus r factorial. So this would have been 100 factorial over 99 factorial and then 1 factorial. So let's plug in 100 factorial into my calculator and let's see what happens. 100 factorial. Okay. Four. Error overflow. It's too big. So even so, if I tried to plug it in, actually it turns out that that's too big of a number. So that's probably not the correct way to do it. It would have been, actually by hand, you would have said, oh, it's 100 factorial. 100 times 99 times 98 times 1 over 99 factorial. 99 times 98 times, cancel, cancel, it's 100. So doing it on the calculator, you really can't do it. By hand, you can do it easily. So actually, I sort of lied because you can actually plug this directly into the calculator and you'll know it. Clear. If you did 100, see if it gives me the last 0. Okay, it said a 0 there. Well, let's, okay, math, go to PRB, it's the third one down, and then 99. It will actually calculate it. So even though it doesn't calculate the 100 factorial, it will do 100 C 99. It'll do that. Okay. Because it's not really doing that calculation. Okay, so Let me show you some of the properties of Pascal's triangle. NC0 is 1. And so, in Pascal's triangle, I should mark where this is. This is page 8, page 7, no, page 8. So this says here that all these terms are 1. And so, NC0 is 1. Well, let's use the definition of NCR. So NCR is just n factorial over r factorial times n minus r factorial. So letting r be 0, it's n factorial over 0 factorial times n minus 0 factorial, but n minus 0 is n. 0 factorial is 1. N factorial over cancels with n factorial to give you a 1. NCN is equal to 1. Well, that just says that this side of Pascal's triangle is always equal to 1. And so, let's do this. So, I have, by definition of NCR, n factorial over, well, r factorial, but in this case, r is equal to n, so n factorial, over n minus r, but again, r is n, so it's n minus n factorial. N minus n is 0. 0 factorial is 1. The n factorials cancel. So again, you get 1. NC1 is equal to n. And so that says that this is n. So notice 0, 1, 2, 3, 4, 5. This always tells you the row you're in, except of course the first one where it's blank. But this always tells you the row you're in. So this guy here. Of course, the other by symmetry, it's also the other side. But okay, so let's show that. So by definition, NCR is just n factorial over r factorial n minus r factorial. So in C1, letting r equal 1, is n factorial over 1 factorial times n minus 1 factorial. But by the recursive definition of n factorial, I have that n factorial is just n times n minus 1 factorial. The n minus 1. In fact, n minus 1 factorials cancel, so you get that this is equal to n. And that's what you wanted to show. I have nck equals ncn minus k. That just says that Pascal's triangle is symmetric. If I look at the middle here, then the lower half is identical here to the upper half. It's just a mirror image of the other side. Okay, so let's do that. So let me calculate NCN minus K. And so by the definition of NCR, I have that it's n factorial over r factorial, which in this case is n minus k factorial, times n minus r. So n minus factorial. Well, let me distribute out the minus sign. So this becomes minus n plus k. The n's cancel, so you just get k factorial. Now let's rewrite this. Let's change the order of the k factorial, n minus k factorial. So this is k factorial times n minus k factorial. So n factorial over k factorial, n minus k factorial, well, that's just nck. And so that's what I wanted to show, that these were equal. Next, n ck minus 1 plus nck is n plus 1 ck. So I have that if you add these two terms above this term, you get this term. So 4 plus 6 is 10. So if you add nck, or well, let's say nck minus 1 plus nck, you get n plus 1 ck. And so let's show that. So let's look at nck minus 1 plus nck. So by definition, nck minus 1 is just n factorial over k minus 1 factorial times n minus k minus 1 factorial. Nck is just n factorial over k factorial times n minus k factorial. Let's rewrite this. This is n minus k minus 1. So let's distribute the minus sign. So this is a minus k plus 1. So let's write this as n plus 1 minus k. So now let's find a common denominator. And so the common denominator will be n plus 1 minus k factorial and k factorial. So this term is already here. In order to get this term, I have to multiply the k minus 1 factorial by k. So let's multiply and divide by k. Now to get a common denominator for this term, well, I already have the k factorial. I have n minus k factorial. So the only term I'm missing in this product is the n plus 1 minus k. So let's multiply and divide by n plus 1 minus k. And so I have a common denominator, k factorial over n plus 1 minus k quantity factorial. For the numerator, well, I have k times n factorial. I have n times n factorial times n plus 1 is n plus 1 factorial. And I have here a minus k times n factorial. Well, the n factorial times k's cancel. So you just have n plus 1 factorial over k factorial, n plus 1 minus k factorial. But by definition, this is just n plus 1 ck. So that's it. 6. Oh, I'm going to use that. Okay. So how do permutations and combinations multiply? And so I have RPK times NCR is NPK times N minus K CR minus K. For 1 less than or equal to K, less than or equal to R, less than or equal to N. Okay, so let's do this. RPK is just R factorial over R minus K factorial. NCR is just N factorial over R factorial times N minus R factorial. The R factorials cancel. So I just get N factorial in the numerator. I have a R minus K factorial and a N minus R factorial in the denominator. And so let me rewrite this as follows. Let's just multiply and divide by N minus K factorial. So this is N factorial over N minus K factorial, N minus K factorial, which cancel, over N minus K factorial times N minus R factorial. So this is equal to, well, n factorial over n minus k factorial. Same thing. N minus k factorial over r minus k factorial. Same thing. Now, I can write n minus r as n minus k minus r minus k. The minus k's cancel, so that just becomes n minus r factorial. But this n factorial over n minus k factorial is npk, and this n minus k factorial over r minus k factorial times n minus k quantity minus r minus k quantity factorial is just n minus k cr minus k. So I should note that the n minus k minus r minus k is just equal to n minus k, multiply the minus inside the parentheses, minus r plus k, the k's cancel, so you get n minus r. So that's this computation here, why these are equal, even though I said it also when I was doing it. Note that in this above, if k is equal to 1, this is the same as r times ncr equaling n times n minus 1 cr minus 1. If k is equal to 2, this is the same as r times r minus 1 ncr equaling n minus 1 times n minus 2 cr minus 2. These are actually, the reason that I wrote them out is only because they're important for other math courses that you may take.